Hello, everyone, and welcome to Signal Systems and Signal Processing with Wolfram U. The topic of this lesson is discrete-time convolution. In this lesson, we'll go over convolution, a mathematical operation denoted by an asterisk between two discrete time sequences x of n and y of n. Convolution is very useful in signal processing as it relates the input and output of an important class of systems called LSI systems, or linear shift invariant systems. If we know the impulse response of an LSI system, the output response of the system to any input signal can be found using convolution. Let's assume that we have an LSI system called S, as shown here, and we know its impulse response, h of n, which is the system's output to the unit sample sequence delta n. Now, for any other input sequence, x of n, using the sampling property of unit sample, we can express the sequence as a linear combination of shifted and scaled unit samples, as shown here. The scaling factors or coefficients are the values of the sequence at the location of the sample sequence. For any sequence x of n, once we express it in this form in terms of delta n, we can find its output since we know the output to delta n. This is because the system is LSI, linear and shift invariant. Using the shift invariant property of the system, the output of delta n minus k will be the shifted version of the impulse response, or h of n minus k. And since the system is linear, the output to the sum of these impulse responses will be the same as the sum of the system responses to each of these sequences, as indicated here. This summation is called convolution sum. Again, using this very powerful formula, we can write the output of an LSI system to any sequence x of n if we know h of n, the impulse response of the system. Let's focus a bit more on this convolution summation. We can easily show that this convolution summation here, the convolution of x of n and h of n, is also equal to the summation shown here, which is the convolution between h of n and x of n. Basically, the convolution operation is commutative. Other properties of convolution are associativity, as shown here, and distributivity, the convolution of a Zn with sum of two sequences, x of n and y of n, is equal to the sum of the convolution of z of n with each of these signals. Also, you can check easily that delta n is the identity element for this operation. Convolving delta n with any sequence gives the same sequence. Now, let's see an example to understand the concept of convolution and get more comfortable with performing the operation through some visualizations. For an LSI system given its impulse response, we want to find the output response of the system to the input sequence x of n as defined here. X of n consists of 4 samples, and so the convolution sum will also have 4 terms, starting from n equal to 0 to n equal to 3. If we break down the summation, the 4 terms can be visualized as shown here. Replacing the values of x and h of n and simplifying, we get the expression shown here for the system response y of n. Using the Wolfram language and applying discrete convolve to x of n and h of n, we get the same response. And we could plot the output to see how it changes over values of n. To compute the convolution sum, we can use the what's called flip and slide method. For this method, we basically slide a reversed version of one of the signals past the other. Let's see how this method works out for our example. First, note that in the convolution sum, h of n minus k as a sequence of time k is a time-reversed version of h of k, which is shifted to the position n on the time axis. Now let's look at the plot of this h of n minus k and x of k here on the left side, together with their product shown in the middle, and the resulting sum for each value of n. You can see how with sliding h of n minus k from left to right across x of n, their product changes, and also the output value y of n. For each value of n, y of n is given by summation of point-by-point products of the two sequences. So for n equal to 0, the convolution sum will be equal to the expression shown here. Substituting the known values of x of n and h of n gives us 1 for y at 0. Repeating the same steps for n equal to 1, we get y at 1. And the same process gives us the remaining values. For finite length sequences, convolution has an interesting and useful interpretation as a matrix operation. If we expand the summation for our previous example for each value of n, what we get is basically a system of linear equations, which we can express in matrix form. The coefficient matrix here called H is a Toeplitz or diagonal constant matrix, which means that each descending diagonal from left to right is constant. Once we replace the values of h and x from the previous example, then to find the output values, we just need to evaluate the product shown here, which can be done using the Wolfram language. Let's show the result in a matrix form. Looking at the set of equations for the convolution of xn and hn, note that for the first and the last samples, y0 and y4, we have a partial overlap of non-zero values of xn with the reversed and shifted version of hn. And for the middle samples, y1 through y3, we have the full overlap of x of n and h of n sequences. This middle portion is called the steady state portion of the output sequence, and the portion including the beginning and the end of the output is called the transient portion of the output. If we denote the length of the two sequences x of n and h of n by Lx and Lh, the number of steady state values will be this value shown here, and the number of transient samples will be Lh minus 1 at the beginning and at the end, making the total number of non-zero samples Lx plus Lh minus 1. For the previous example, we can use the function least convolve of the Wolfram language to compute the output values, as shown here. As you can see, the result has only the steady state values. To get all of the values, steady state and transient, we can use the third argument of the function least convolve, 1 and negative 1, as indicated here. The fourth argument is for defining the padding value. Choosing 0 padding, here are all the values of the output. As another example, let's look at the moving average filter, a popular method of smoothing noising data. The unit sample response of the averaging system is given as shown here. The smoothing effect is obtained by locally averaging the input data. For this example, let's look at the daily, weekly, and monthly temperatures in the city of Portland. If we extract the raw monthly temperature data and smooth the data by convolving it with the moving average filter, a constant sequence basically of length 5, you can see the effect of smoothing in this second plot. And here you can see the same effect for varying values of n, the length of the filter. Let's look at one more example where we have two infinite sequences for x of n and h of n, and see how we can evaluate the convolution sum to find the output using a divide and conquer approach, where we basically break up the region of summation into non-overlapping subregions. First, let's compute the convolution using the Wolfram language, as shown here. And let's plot the result to see how the output sequence changes over time. Now, to perform the convolution by hand, if you look, you will notice that for n plus 3 less than 0, there is no overlap between h of k and x of n minus k. And so the product of the two sequences inside the summation is simply 0. Y of n is 0 for this interval. But when n plus 3 is greater than or equal to 0 and n minus 3 is less than 0, equivalently n is between minus 3 and 3, we have a partial overlap as you see here. Therefore, the convolution sum can be expressed as shown here, with limits of the sum being 0 on the left side of h of k and n plus 3 on the right side of x of n minus k. This gives us the output value for this subregion. For n minus 3 greater than or equal to 0, we have complete overlap between the two sequences, h of k and x of n minus k, with the limits of summation being n minus 3 and n plus 3. For this interval, we can find the output by evaluating the convolution sum shown here. Finally, using these values for 3 subregions, the output at any given n can be expressed as shown here. In this lesson, we analyzed the convolution summation. Through several visualizations, we saw how the convolution operation works and how it could be computed using a divide and conquer method. We also use convolution to find the output of an LSI system for any input sequence x of n, given the system's sample response.